Hey folks, welcome once again. We find ourselves in Chapter 7, Section 2, talking about properties of gases and the gas laws. So I'd like to start off with what is a gas, right? Before we talk about the properties of gases, the gas laws, what's the theory behind gases? And that's currently the kinetic molecular theory. The kinetic molecular theory describes or explains how gases behave. The first point is that it says gases are moving in constant random motion. They are going at very high speeds in straight lines, right, until they hit a wall. They just bounce around randomly and fast. The actual volume of the gas particles themselves is negligible, right? So the volume is clearly not zero, but we're going to say that relative to the container, which is, let's just say, macroscopic scale, right? Something maybe you can hold in your hand. The size of the particles themselves, even if you have a lot of them, is negligible. Okay, next, there are no intermolecular forces between gas particles. Essentially, they're moving too fast and they're too far apart, right? And these two kind of go together well, because if we think about, say, us in a classroom, right? If we get up and start moving around in random motion, of course we're going to bump into each other, right? And when those collisions occur, right, there will be some forces of attraction or some energy or something will happen, right? But if we now take ourselves and put us onto a football field and say move randomly, right? The chances of us interacting are go down by a lot. And if we now say like, okay, now take yourself, our classroom of people across the state of Iowa and just start moving randomly, right? Now, the actual space that I take up while standing where I am standing is negligible compared to the state of Iowa. And you, as a gas particle across the state somewhere walking around, and I, as a gas particle over here where I am and across the state, don't interact, right? So that's kind of the scale of things to think about. Okay, and the final point is that the temperature depends on the average kinetic energy of all of the particles. So this is a theory, right? If you recall that theories explain, a theory is like a model that tells us how to think about something, and a law describes. So notice this chapter is called Gas Laws. So we're going to be describing gases and how they behave without having to know the theory behind it, but the theory explains why we see the laws that we see. Okay, so that's the kinetic molecular theory. Now, if we wanted to go look at a gas, what kinds of things can you measure about a gas? Scientists like to measure things, right? So, what can you measure about a gas? Now, we have no interaction on this video, so I want you to just think about this for yourself. And you might come up with a list like this. We can measure the pressure, volume, and temperature. And then another thing that may be a little bit harder to come up with on your own is we can also measure the number of moles. Right? We do this indirectly by weighing it, but that is something that we can measure. So that's pretty good for gases. Gases are well understood experimentally, mathematically, and also now theoretically with the kinetic molecular theory. So to kind of like break all those apart, right? People did experiments on gases, measuring pressure, volume, temperature, number of moles to see what happens. Then they were described mathematically to see how the properties were related, and then explained why that was the case, theoretically, through the kinetic molecular theory. So let's take a look at one of the first experiments and one of the first mathematical relationships, which was derived by Robert Boyle in the 1600s. And he was measuring pressure and volume relationship. Now, I think nowadays to us, this is almost so commonplace, it's intuitive, right? But at the time that he was doing these experiments, no one had really technically measured these kinds of things before. No one had figured out this relationship. And no one had put a relationship like this to be expressed mathematically in the form of an equation. This was one of the first to do that. So here's what he had in his setup. It's called like a J-tube, and you can see why. Right? And one end is closed, and this end is open, and it's full of mercury, which is a liquid metal. And so the mercury pushes down because of the atmospheric pressure, right, coming in through the open tube. And that causes whatever air is in here to be trapped. And that will push back, and we have equilibrium, right? There's an equilibrium between these. And so the the amount of mercury is a proxy for the pressure, right? Because as we see here, if there's more mercury, it's heavier, pushing down, and the pressure here is going to be impacted by the amount of mercury. So basically, he set up this experiment with different amounts of mercury, which are essentially different amounts of pressure, and then measured the volume of the gas at the end, closed end of the tube. And so when we have, let's say, atmospheric pressure, 760 millimeters of mercury, the volume of the gas was just, we'll call it V. When the pressure was doubled, the gas volume was half as much. And when the pressure was tripled from case A, the volume was 1/3 as much, right? So this was actually a beautiful and surprisingly simple relationship. That's just a linear inverse relationship. And this became known as Boyle's law. Boyle's law says that volume and pressure are inversely related. And so as one goes up, the other goes down. This figure here uses the mass, again, as a proxy of pressure. So it makes a lot of sense when you see it this way. A larger mass here pushes the piston farther down, right? So that's increasing the pressure, and the volume goes down. We can plot these on a plot as volume versus pressure, or where we see a curve, or 1 over volume to pressure, which is a straight line. And if volume is proportional to 1 over P, we could say that PV is proportional to 1. Now, it could be 1 with the right units, but if we have whatever units they are, this value would change. But the point is, if some other set of pressure and volume must also be proportional to the same constant, which means that these two are equal to each other. And that's where this comes from. So P1 V1 equals P2 V2 if the number of moles and the temperature are held constant. That's Boyle's law. All right, here let's do some examples. So Boyle's law actually helps explain breathing in a really cool way. So when you want to breathe, take an inhale, the diaphragm will move down, and the movement down of the diaphragm expands the lungs. So volume goes up, which makes pressure go down, right? When the pressure goes down, air flows in to balance that back out. And then exhaling, diaphragm goes back up, the volume of the lungs decreases, which makes the pressure increase, which pushes gas out. And that's exhale, and that just keeps going. So Boyle's law, the PV relationship, helps explain lung physiology. Okay, here's a question. We're going to have a lot of questions of this type. A helium balloon with a volume of 1.1 liter and a pressure of 0.91 atmospheres expands to 3.1 liters after being taken into the mountains. What's the new pressure, assuming no change in temperature and no gas has escaped? Okay, we're going to have a lot of questions like this. I want to go through a few steps of how to solve these problems. So first, determine the three given variables and the variable asked for. So it's always going to be something like, let's say P1 V1 equals P2 V2, and three of them you will know, the one you'll be searching for, right? It could be a different relationship, which we'll get to, but so write out the equation, rearrange it for the asked for variable, plug in everything that you have been given, and carry out the math. Check that it makes sense. You don't have to do it this way, but I do suggest you stick with the variables until the end. Some students like to start immediately plugging in numbers, and maybe that works, but I'll tell you that this definitely works. Okay, so back to our question. Let's see. What do we know? We have an initial volume of 1.1 liters, an initial pressure of 0.91, get my dot there, atmospheres, and it expands to 3.1 liters. What is the new pressure? Okay, so we can see the relationship is between P and V. We're solving for P2. So if we divide both sides by V2, we now have an equation for P2. And all three of these are the three that we have here, right? So we can say P2 equals 0.91 atmospheres times 1.1 liters divided by 3.1 liter. I like to put the parentheses just to help separate out the different variables, but it's not really necessary to do that. And then we just plug this in and notice that the liters cancels out and we're left with atmospheres. There should be 0.32 atmospheres. So then remember, check, does this make sense? So volume went up, so we should expect pressure to go down, and indeed it did. We could even see volume went up by approximately a factor of 3, from 1.1 to 3.1, and pressure went down by approximately a factor of 3. So yes, it all worked out. And here for your reference are some of the notes, but we just walked through this. So it shows the steps, and there's the answer. All right, we'll stop part 1 and come back to talk about a couple more of the simple relationships of gas laws in part 2.